Yeah, let's proceed,
Okay.
George.
Okay. So again, my name is George Prun, and I'll be moderating this second invited project session. This is, as I mentioned before, these are some of the projects that are not cross-border projects, but they have indeed, and as you can even see from some of the names, have clearly a CAM focus. So the presentations will be on the project or on part of the project that relates with CAM. We are very glad to have here the presence as well of the Chinese 5G large-scale trial twin project to get a perspective from what is going on in China. So without further ado, I hope that Marcus is there.
Yes, George. Good afternoon.
Hi, Marcus.
Good afternoon,
Welcome.
everybody. I'm here.
Is Marcus?
Yeah, thanks, George, for this kind of introduction. And I was the technical manager of the 5G car, and this project basically dealt with business case analysis. So this is, I think, the focus on the talk today. And to give you some background first on the 5G car as such. So 5G car had several use cases in mind: lane merging, see-through, network assisted, variable pedestrian protection, HD map acquisition, and remote driving for automated parking. So you could say that these services are part of the CCAM service portfolio, and you need to provide these kinds of services, maybe not all of them, on the roads, on highways, like for example lane merging, like see-through. HD map is certainly one key element, and also recently telebrated driving is seen as level 4, level 5, maybe enabler to support the vehicle in critical situations. And this drives, of course, bandwidth requirements along the corridor, along the highway. And we have to analyze, actually, is there a green light? Do you get any money back if you invest in 5G along corridors, along highways or roads? Or you will come up with a deep red after maybe 5 years, 10 years, and so on. But 5G car had more than only, let's say, business case analysis. It also was the first project where the car industry trialed the telecom industry in a joint project. So we had here PSA, Volvo, for instance, here Bosch. Then we had the typical suspects, Ericsson, Nokia, Huawei. And these two big, I would say, camps tried it the first time to work out the 5G V2x technical architecture requirements. And this was quite useful to get an insight from the OEM colleagues to really get that deep understanding. And certainly we are way ahead from the level 4, level 5, but I still believe that we can do it the next couple of years. So all this stuff considers 5G V2x, or you may also call it CV2x for cellular V2x, which has two components. One is a direct communication on the so-called PC5, and the other are typical V2N UU-based communication, where you use edge computing or cloud computing to engage the vehicle. And this we may also call extended vehicle concept, where you have some onboard processing, but also you have some further processing in the edge or even the central cloud. And we had, when we started 2017, the view that we need very ultra-low latency and high reliability to perform, for example, platooning and other very mission-critical services among the cars. And this was the focus here of the project. So let me then continue. And now we come to the actual topic. I think the 5G CAM highway roads considerations, we need some basic background. And this background you see here on the next slides. So one background is the question, how intelligent is the highway? Is it a very stupid road or a very intelligent road? And the project Inframix, I think this project concluded last year somewhere, has defined 5 different basic levels. So from level E, actually typical roads today, there's nothing, only the driver and the road surface. Then you have already some basic support in D with HD maps. You can further on with C, B, and E is actually the highest level of intelligence, where you have a full support from the infrastructure to enable corporate driving. So to align maneuvers, to exchange information on corporate perception. So basically you see here on the right side the upgrade of the intelligence. And what we did actually was the level A analysis, because we assumed this could be the most expensive, let's call it, highway or road segments. And when you see on the market perception from several analysts, here, for example, smart highway markets from last year, they see a clear necessity and an uptake in smarter highways or smarter roads. So when you go to the communication system, which could be 5G, could be also, let's say, roadside units with the 5.9 spectrum, then you see 21% every year on increase of market sizes. And of course, you can now also discuss where are these, in which countries. But more important is here the communication system. And of course, there are other uptakes. Monitoring systems must be more invested. And it's clear when you invest in one component, this requires also investments in the other components. So we see a clear trend that the smart roads, highways, whatever, have an impact in Europe. But it's a long way to go, colleagues. You see here how fragmented are these different standard setting organizations for CCM. So it's alone for Europe. I think it's 20 whatever, and then you have for the complete landscape, I think there are 30 icons here, or 13 acronyms on the right side. So it's very, very difficult because these organizations must work together to come with a single solution, because it's clear, and every highway segment and every road segment in Europe must perform the same. And these different organizations must contribute to the ultimate goal of CCM. But you see from the pure number of organizations how complicated this world will be. And what is also missing here is the 3GP. The 3GP feeds into that solution space, for example, in ETSI, CCSA, 5GA. So it's getting very, very complicated. But we have no other, I would say, opinion than to agree on these different organizations. Now, when we come to the infrastructure, or call it ISAT, infrastructure supported automated driving, we see here different, I would say, hardware deployments. First of all is the base station as such, the roadside unit, which may work in the 5.9 ITS spectrum, and then you have the so-called V2N base stations, which are also somewhere close to the road. Then you have edge server, you have a cloud server, and you see basically some initial signaling between, I would say, the car, the level 3, 4, 5 car, the edge. And here I think is the major traffic between the two hardware boxes, I would call it. Of course, the base station is somehow embedded in the edge here, and this requires certainly some investment. And you see on that table the spectrum requirements for these different services. So there is one component which we call vehicle entertainment. This, of course, is not important for the CCM, but all the other services here, you could see this as part of the CCM service aggregation. Of course, software-defined or software update is also very special and has nothing to do with CCM. But all the other services require a strong uplink, and at the end you have several hundreds of megahertz, depending where you are, rural, urban, or dense urban. And important is also that fact that the infrastructure-assisted environmental perception, this is exactly where you offload from the car, maybe a raw data sensor, to the edge, you get back the object lists or actuation commands and so on. But this requires, as you see, a huge, more or less, bandwidth requirements in both directions. And this is one of the also pain problems. This is usually then licensed spectrum. And you can imagine the operators would be quite happy to earn so much money. And but we have to see whether this can be really implemented, or we have to go into new ideas where we find spectrum, maybe millimeter wave, maybe terahertz communication, maybe even 6G, whatever spectrum. could be part of this story. When it comes to China, in China, I think we are lagging here behind in Europe. In China, they already have specified some concrete requirements for smart highways. For example, the localization requirements you see here. Then requirements on latency, broadcast mode, unicast mode, packet loss error rate, and so on. Already there are specifications on the way, but also on cybersecurity specifications. And when you go to the smart highway back, you see this different, I would say 6 different or 7 different vertical solutions. You need to work together, you need to combine together to provide really this automated driving down to every single vehicle. And this is quite interesting to see these specifications, unfortunately all in Chinese. So translate some of them in English. I hope the grammar is correct. But in Europe, we are lagging behind that situation. Also, Europe must come up with similar specifications. What is a smart highway? And remember, we had these 5 levels from A to E. And I think we are not yet on that page. Now, when it comes to the business case analysis, what we did in 5G car, we also acknowledge that we have on a single 5G, not only 5G cam, but also infotainment. And the message here is basically that you can allow roaming. So in this highway segment on the left side, which may be 100 kilometers long, you allow the operator 1 to operate and to provide 5G cam services. Then for the sake of being fair, you have another segment where you hand over this functionality to operator 2. And then in the third one, you can bring it back to operator 1. And this calls for a dual SIM approach in cars, which nowadays is at least in expensive cars is the case, that you have one SIM card for the infotainment. You have a SIM card which works on the 5G cam as well. And you can more or less make roaming between these segments. So this is important to consider that the 5G is not only there for 5G cam, but also infotainment. If you want to save more money, you can use the 5.9, which is free of charge, where you run the day 1 services, the safety messages. And basically, you can also do this over the license spectrum, but then you need additional 10 to 20 megahertz spectrum for the license one. And then, of course, the operators will charge you again for safety messages. This is one of the problems. But in our situation, what we did in 5G car, we only looked on the V2N. So we did not consider the RSU deployment because this is also very expensive. What we see, for example, in the Italian ANAS deployment, they talk about 350 meter distance between RSUs. But here for 5G sites, we have maybe 1 kilometer or even more. So from business case point of view, the 5G deployment may be more meaningful. And of course, the services here are also in blue here. I mentioned this already. Coming out to some figures. When you go to the cost analysis, what are the costs for 100 kilometer to deploy these 5G cam services? You see clearly here that the sites are more or less 100%, 90% of the money goes into sites deployment. And what you can neglect is the spectrum costs. So we assume, for example, for Germany, some costs here on the 3.x on the C-band auction based on 2019, and this is very small peanuts. The MEC costs may be required for every 20,000 road kilometer size is also peanuts. The supplementary services, for example, positioning, TOD, HD maps, so these are horizontal services, are also negligible. Service provider costs, you can forget. More expensive could be the TOD human driver. So in case there's a problem with the vehicle, the human driver must have been for remote takeover. But all in all, it's remaining the 99% of the sites. And for these sites, it's also clear we do not start from scratch. We have existing LTE sites. We can upgrade to 5G. But basically, we have 80% of new sites. So every kilometer is the goal to have, let's say, 1 site. Comparing this with the road building costs situation, when you go to Germany, for instance, or I don't know, maybe in Europe, it varies between 600 million euros and 2 billion euros per 100 kilometer building costs. So actually, the 5G site costs versus the road costs are somehow in the 1%, maybe maximum 2%, depending when you have many tunnels. Of course, the costs go up. So in all, this one single site is about 100 kilo euros, what we have assumed. So the actual 5G site, civil works, fiber backhaul, network operation, site lease. This is, let's say, the major part of the 5G CAM deployment. Now, on the next slide. So the business logic is actually that you as end driver, you apply the service pay as you drive. So you are somewhere on the highway, you enter a zone where pay as you drive is possible, you press the button and then start reading a newspaper or doing some other stuff. So the end user will pay money to the CAM service provider. This CAM service provider, of course, has to pay in turn other service deliveries, HD map, TomTom here and so on must be paid. But at the end, also network operator wants to see some money. So some communication fees go into his pockets. And then we assume there's also collaboration between road operator and MNO, because the road operator has in many cases already dark fiber deployed, power cable deployed along the highway. So the MNO can make use of that road operator deployment. This we call passive infrastructure sharing. And this is basically the logic here we use for the analysis. For the deployment, I already mentioned network sharing. So you see in this later on, but here on this column, you see actually a single operator is doing everything. So here, in this cell, basically the network operator is also running the active and passive parts. Here in this cell, the network operator shares passive infrastructure from road operator. And then we have the situation, we call it revenue 2, where we have multiple MNOs involved. Here in this cell, operator is doing everything, passive, active, but does not share anything. Here in that cell, we have multiple MNOs, but they have a common passive infrastructure from the road operator. And basically it's here that you share everything. This would be also active sharing, spectrum sharing, then passive sharing. This of course quite unlikely that we will see active network sharing. But nevertheless, for the costs analysis, it was quite useful to understand what are the benefits of sharing as such. So this is basically the last slide. You find more information in this publication from 2019, but the logic is still, I would say, up to date and valid for today. So coming back to these different streams. So this is the solid lines are the actual TCOs, total cost of ownership, including CAPEX, OPEX, what we just discussed per 100 kilometer. Here you see the income, the dotted yellow line, or you see here the purple dotted line where the income comes later. So when you cross this TCO, you get a positive cash flow. So you see your return of investments here after maybe 2.5 or 4.5 years. And coming back, deployment 1 was actually an operator doing everything by its own. Then you see basically a later return to positive zone compared to people who want to share, maybe the passive sharing. So they can come back to the positive cash flow situation after year 4. And if you want to do everything by your own, which basically is this revenue 2 on the right column, maybe you call it, then you could have situations where you never get back money and you have to wait maybe 15 years and then of course banks get quite nervous. So the lesson is actually sharing brings you a benefit and you can come earlier to the, let's say, green zone. And basically here are the working assumptions again. So we have this 100 sites. Then important is you must go to a highway where you have many cars, not just one car per day. And it's clear we assume there will be also a yearly penetration rate where you see every year 10% more intelligent cars being able to consume these CAM services. And when you go to the service costs or the fees you have to pay, so this was very interesting. When you pay €1 as driver for 100 kilometer highway segment, you have to pay 50% of that money to the connectivity and CAM service costs. But having this small money in mind with such a huge number of cars and this even 10 million investments for the 5G sites, you are able to make money after 4 years, 5 years, whatever. And compared to the road construction costs, is very negligible, this 1% extra costs or the 5G CAM service deployment. So this is important to understand. There are also some I would say, work or play around figures, increase, decrease of costs or whatever. This is not so important to memorize, but the major takeaway is sharing of passive infrastructure brings you benefit. You may go into roaming agreements that you have different segments where different operators work on that to be fair, on a fair basis. This would be, at the end, most beneficial for the end user, the driver. Good. I hope the message came clearly over to you, and let me know if you have questions. Thank you for your attendance.
Thank you, Marcus. So questions, let me see if there are some questions. Okay. No, but I have a question. Looking at these sharing alternatives, from no sharing to active sharing, did you do an analysis, or in which countries this would be possible? So do you have an idea or where this could be applied? And also, what would be the impact of national roaming? You mentioned in one of the slides national roaming, but it only exists, or there's been in the license conditions in, if I remember correctly, only 2 of the member states. So
yeah, so first part of your question, no, we did not consider a special country, I think, but the deployment costs, what you see are, for example, the spectrum costs in Germany. Here's the background Germany, so it may be different in other countries. The OPEX costs, the manpower costs, labor costs are different. So we assumed here Germany basically. It may be completely different in different parts of the EU. And what was your second part of the question? The
yeah, where is there national roaming?
Right. So for the roaming, actually, we didn't assume a special country, but when you assume, for sake of being fair, if you would have 5G CAM services not only by one operator, if you split it to different operators, you have to, at the end, to pay more for the end driver. If you give it to one guy, then suddenly he makes most of the income because he charges all the drivers on the same highway segment. But to be fair, maybe the other following segments, you hand it over to another MNO, also that this MNO can make money out of that. So this was the only point we considered. In that case, there would be roaming required only for the 5G CAM, not for infotainment. But this was also an assumption. It was not based on a concrete country in Europe.
Okay, there is a question that has to do with the costs that you mentioned, the comparison that the telecom costs for the deployment of CAM is around, it's less than 1% of the costs of the road infrastructure. But if the road infrastructure is there, the difference is that the road infrastructure is there, but the CAM needs to be built in. Can you comment on this?
Yeah, let me try to, I think this was probably this slide here, right? So what we see here, that the RAN infrastructure is, or the sites, you may call it, the 100 sites, is 99% of the total costs. And of course, the service costs is somewhere running in the cloud service. Okay, you need to develop the software. It's clear you need to operate the software, but this is software you share with all the highway segments, right? So here would be only the scalability would be a question, that you need to provide more processing power on the edge computing, more or less cloud servers. And this is at the end also not that big. Of course, you need to develop somewhere the software, but compared to this 100,000 euros you pay per more or less per site, so this is around about 10 million. If you invest this money or a little bit money for the software development, then you end up in this low costs, okay, like whatever 0.001%. And moreover, the software can be duplicated to all kinds of road segments in Europe, right? So this is a single software, like Microsoft Windows. You know, they sell it many times, but they have a big, more or less, revenue based on this selling software. And compared to the actual construction zone costs, it's about 600 million and 2 billion. So the extra side cost is this 10 million on top is very tiny. Okay, the only problem is you must find someone who is willing to pre-invest in these deployments. Every kilometer, one 5G site. But I see a synergy for infotainment. So you do not only provide it for CAM, but also infotainment. And because of slicing, you can use the same hardware for the different, I would say, endpoints in the car. One is for the passengers and the other is for the machine.
Mm-hmm. Yeah. I think so. Part of the point is that if the OPEX costs are a certain percentage of the total CAPEX, the maintenance costs of roads are again the same order of magnitude higher than the 5G OPEX costs. So this is an important issue. Yeah. The other thing is that you assumed in your analysis a growth rate for penetration of around 10%, which for me seems a little bit excessive, at least, or very optimistic, at least at the beginning. What is you already said that you are confident that autonomous driving will happen soon, but what you mean soon? Soon is in 10 years or in 20?
I would say, you know, on private grounds, in harbor areas, airports, maybe it comes earlier, interval driving, for instance, like this automated valet parking. As you know, there's already solutions on the market. You see it in television advertisements from Bosch, for instance, that you park your car in front of the parking garage, and then the EVP system takes it up to floor 3, 4, 5. So this already is available. It's an early, I would say, automated driving flavor for parking garages. If this, of course, of Corona is still working out, that you have to rush to the airport, to the airplane later on, I don't know. But when it comes to public roads, I think this takes more time. In China, probably will happen much earlier because of the excellent 5G coverage along these highways. And 25, 26, we see more increasing services, okay, for that. And here the network-based driving increases the safety of level 3, 4. But level 3 still has a problem for the regulations part. So the government must be fully convinced that it works in every weather condition. And this technical wise, things are there, but for the OEM point of view, it's still very difficult to get the exception of regulations, so that the government is really allowing these cars to drive on public roads. On private roads, then things will come much earlier. Maybe in 2 years, 3 years, we see things like TOD, then shuttle buses on the air-ground field. But in public areas, when you have special lanes, then you could also allow these shuttle buses. And you see it already nowadays in urban areas in Sweden, that you have autonomous buses which would drive around in certain city quarters. So it's already there, okay, even for these shuttle buses. But of course, they run at low speed, and I don't know what they're doing when they have bad weather condition. So this is the current situation. It will come gradually, starting from certain areas.
Yeah. Okay, Marcus, thank you so very much. We need to move on. Thank you so much. Let me again share my screen. So we will now move to the presentation of the project 5G IANA. The project will be presented by Vasilis Surlas is a senior researcher from ICCS in Greece. Sorry. He received his diploma in engineer and Master of Science in Computer Science from the Computer Engineering and Informatics Department of the University of Patras in 2004 and 2006, and his PhD from the Department of Electrical Computer Engineering at the University of Thessaly in 2013. He joined the UCL London for a Marie Curie fellowship in 2015, and since 2017 he's been working in ICCS, National Technical University of Athens, in the iSense group. He's participated in a number of EU-funded projects, and his main interests are in the area of computer networking and future internet architecture. So I give the floor to Vasilis, please.
Thank you very much for the introduction. I'm not sure if you can see the right screen or the wrong screen. Can you see my presentation or not?
It will go now. Yes, you are there. Please go ahead.
No, we see your desktop, so we see another screen.
Ah, okay. Let me swap them.
That's it.
You still can't see it? You can still see the wrong one?
Yes. Yes, you just need to change the display settings at the top.
Okay, I'm just going to remove the second screen just to make sure that everything is fine. Okay, sorry for that. Yes, thanks again for the introduction. I'm going to present you and I'm also going to turn off my camera just to make sure that everything is fine. I'm going to present you a project that hasn't started yet. We're moving from a project that has finished to a project that will start. The technical work will start this September. The project is called 5G ANA and stands for 5G Intelligent Automotive Network Applications. The project is part of the ICT 41 projects, but it's very strongly related to this CAM, as George mentioned in the beginning. It's composed by 16 different partners from 8 different member states, and 10 out of them are SMEs, so we're very happy about that. The duration is 36 months, and it will start, the technical work will start, as mentioned, this September. Now, the scope of the specific project is to provide an open and enhanced experimentation platform that will provide 5G network resources, on top of which third-party experimenters, mainly SMEs in this call, related to the 5G PPP automotive vertical, will have the opportunity to develop, deploy, and test their newly developed services. In order to do that, the 5G ANA will propose an automotive open experimental platform, as we call it, that it is the whole set of hardware and software resources that provides the communications and the computation infrastructure, as well as all the necessary management and orchestration components needed for the 5G networks, in order to support, let's say, the developers of the new network applications. This is also coupled with a NetApp toolkit that will expose to the network experimenters secured and standardized APIs that will allow them to facilitate all the different steps towards the production of a new service. Part of this network application toolkit, besides the templates and all the necessary tools to change their applications, it is a new automotive VNF repository that will continue all the necessary VNFs that are useful for the automotive world, mentioning all the different messages that are changed within the car, within a vehicle, sensors and components, and outside of it. So this is very critical, so that SMEs or users or developers that are not fully aware of how those systems work, they can use it and provide their applications. On top of that, we are also proposing, due to the specific nature of this automotive world, a distributed AI machine learning framework that will provide functionalities for simplified orchestration of collections of different AI/ML service components. And this is very interesting and very useful and very important for us, because the automotive world has this privacy nature, and on top of that, we are talking about moving UEs, moving components, moving vehicles that produce huge data sets of data. So it is really important to provide AI and ML techniques at the very edge of the network, so that you don't have to transfer all this huge data somewhere in the central location. In order to provide this functionality, 5G ANA will enable different MANO frameworks besides the traditional, let's say, 5G standalone network and the MEC and the edge components. Will also be extended to the OBUs, referring to the onboard units of the vehicles, and to the RSUs, referring to the infrastructures at the site unit. And this will be done with a containerized and virtualized onboard unit that will allow us to, let's say, extend the borders of the network down to the cars and the vehicles itself. Besides that, in order to demonstrate our activities, we'll have 7 automotive-related use cases tested in 2 different well-equipped 5G standalone testbeds. A very important part of the proposed projects is also the multi-stakeholder cost-benefit analysis, since also to the nature of this ICT 41 call, it is to enable SMEs and newcomers to get into this 5G world, and especially to the automotive world. Here are some more specific objectives, which there's no reason to go into much details. Besides the technical details and the KPIs for the specific objectives regarding the technical part of the project, one very critical part it is that we are going to enable coexistence with different communication techniques besides the 5G network, because whether you like it or not, there is already some ITSG5 and the V2x developments already in the automotive world. So it is important for the OBUs and the RSUs to be equipped with different models that can interoperate with different communication schemes. Also, a very critical point for our work in 5G ANA is that we are targeting to improve the service creation time from minutes or hours down to some seconds or some minutes, which is also very important in this field. And of course, let's say an aftermath of all those activities, it will be the increase in the road safety and the reducing the carbon footprint that comes from a well-developed automotive sector. Now, this is pretty much the automotive open experimental platform that I mentioned before. This is a schematic depiction of it. And it is composed, as you can say, from 2 different parts. One, it is the orchestration part, that it has this Node SM and MSO components that I will explain later on. It is the virtualized infrastructure domains, that it are the OBUs and the RSUs from the movable, let's say, or from the roadside infrastructure part. And of course, the 5G networks that brings them all together. As you can see there, there's a box which calls Automotive VNFs Repository, which is composed of different baseline VNFs that will be provided and will be developed by the consortium. And of course, some very useful communication VNFs, both short-range communication VNFs for the components within the vehicle and for the components on the road, and long-range communication VNFs to enable the 5G, let's say, communication. Here I'm going to give you some more details on the different, but will not spend a lot of time on the different components of the NetApp orchestration and development framework of the 5G ANA. Here you can see some more details of the different components. On the lower left hand, you can see the network application toolkit that I mentioned, where will facilitate the VNF repository that I showed you earlier, and of course we'll also provide different templates in order to chain, in order for an SME to chain its network application. The node pretty much is responsible to take care of the network applications from the application's point of view. So it is in charge of handling the whole lifecycle management of a NetApp from the moment that it was requested by the application provider up to down to the time that it is deployed on the network and down to the vehicle. On the other hand, the SM is in charge, let's say, of the networking part and the lifecycle management of the network applications, and it has the responsibility to take, let's say, get the requirements for the network application from the networking point of view and find the necessary networking resources on the underlying physical networks in order to enable then, the corresponding slice that will facilitate the corresponding network applications. Finally, the MSO is responsible to, let's say, organize and orchestrate the different network applications, the different network slices that will run in parallel on top of the network. And this is also very important because it can react, let's say, real time and provide more resources to a network application when it's needed, or reduce some of them, or reallocate the chains within the network, the underlying network. Now, the 5G ANA toolkit and repository, as I mentioned, it is a whole set of VNFs that are either have been already been developed in other 5G related projects, or have been developed in different forms in different automotive related projects to works. But here we will try to let's say gather them all together and provide them to SMEs in order to provide, chain, and create new network applications. Out of which we will develop and we will provide 6 automotive-related communication VNFs and 31 automotive-related baseline VNFs. And in order to showcase that these are useful, all the 7 different intelligent network applications that will form the set of use cases to be executed will chain at least once the proposed VNFs. Here I have some more details, but there's no reason to tire the audience with more details from that, about what kind of VNFs are to be implemented. You can see that for the communication of VNFs, we have included all the necessary CITS related messages, both short-term, short-distance and long-distance communication VNFs, which are very important in order to facilitate the automotive world and the 5G world. In the baseline VNFs, you can also see the first set of the VNFs that are to be developed are the EDGI-related VNFs, and are pretty much all the messages in the automotive world that have already been standardized or are to be standardized. In this slide, you can see also the rest of the baseline VNFs that are to be developed, but with red color, we have a VNF, which is, in our opinion, very important because it is a simulator of all the different EDGI cooperative awareness basic services. This means that it's a simulator that will simulate all the different EDGI automotive-related VNFs that we hope that it will be useful to SMEs to take them, use it, generate different SMS, different messages in order to check if the network application behaves as it should be before being deployed and further developed and be deployed in a real-world vehicle. The final 4 VNFs there are those VNFs that will be used in order to facilitate the distributed machine learning framework, and it is the standard, let's say, components that you need in order to provide this distributed machine learning and AI framework, which are the parameter server, the aggregation node, the training agent, and the orchestrator that has to be deployed appropriately within a network in order to facilitate these activities. Now, the 5G IANA DML framework has been, let's say, inspired by the federated learning scheme proposed initially by Google, where the actual machine learning process, the learning process of a model, it's been done at the very edge UE. So there's no reason, either to flood the network with all those of data, which in the case of automotive world, there might be hundreds of gigabytes due to the LiDAR or the radar or the cameras that are using. And on the second and most important reason is due to the privacy reasons, because you don't want your data to be flooded across a network and up to a cloud or to a service provider that you are not even aware who is it. So the idea here is that we provide all the necessary tools so that something that can be trained at the very edge and only the parameters of the machine learning algorithm can be sent to the central locations for the aggregations, can be used by the corresponding SMEs. Also, we're also looking into different hybrid, let's say, techniques where both the machine learning and the inference can be executed in various different layers, either at the car vehicle itself, or the RSUs, or at the MEC, or even at with the traditional way at the very cloud of a service provider. Now, the use cases of 5G ANA have been categorized into those 4 different categories, either as a hazard notification use case, or a vehicle movement use case, or a smart traffic planning, and also for an infotainment related use cases. And below you can see the 7 different use cases that are to be executed in the 2 different 5G standalone testbeds that we have in the project. The reason for choosing them is because of their inherent difficulties and the need to have 5G coverage and 5G connectivity. And of course, in order to use at least once and to chain at least once all the different communications and baseline VNFs that were presented before. I'm not going to spend a lot of time to go into details in all of the different 7 use cases. I'm only going to showcase you a couple of them. Let's say the first use case, which we call remote driving, is a well-known, let's say, use case where a vehicle is controlled remotely via 5G network. The target TRL is to reach target 6 starting from 4, and besides the key KPIs, which are the standard KPIs like latency, user experience, data rate, etc. We also target with this modular and VNF based scheme to decrease the service creation time from what it is now around 30 minutes into a less than 5 minutes target value. So even if this application is not up and running for a specific car, when it is requested, it can only take less than 5 minutes or even lower to be deployed at a specific location. The same pretty much occurs from another very traditional automotive-related use case, which is called maneuver coordination for autonomous driving. Also here, the target TRL is extremely high from where we are starting, and the creation time is also targeted to be below 5 minutes or so. Here I have also included a use case which is called network status monitor, which is going to be used mainly to test the distributed machine learning scheme and framework that I was presented to you before. It is going to be used as an automotive use case also, because the predictive quality of service, which is based on accurate network status monitoring, it's very critical in order to have a seamless, let's say, and smooth use of any kind of automated driving functionality. But we are mainly using it here just to showcase that the distributed machine learning is operating appropriately. Now, as you can see, in all the use cases, we have specific impacts yet and business and per use cases, but the general expected impact and one of the most important target impacts is to minimize mainly the creation time and minimize the cost for building new services, which is very important here. What we were missing in this call, and it was not available it was not part of the requirements when we were preparing the proposal, was an open call, because this will have been a very good opportunity to allow external SMEs outside of our consortium to join forces, let's say, later in our work, and create their own applications, their network net apps, using our VNF repository and using our experimental platform. Since we couldn't have done that extensive this activity, we have included some small, let's say, testing open source projects, 3 of them, so where we can showcase that how easily you can build your own network applications. And this is the end of my presentation. So I hope that it didn't take too much time.
Mhm.
And we can
No,
accommodate questions.
thank you so much. Thank you for this presentation. Yes, your focus is very much on the camp side, but there are other projects that also looking into this service creation issues as well. So I would call your attention for the project, at least for the project 5G ASP, so which is also dealing with this type of questions. So but it's very interesting, especially the KPIs that you have listed are extremely interesting. Since I have no other questions, I thank you again for your contribution. Thank you so much.
Thank you very much. Looking forward for starting this work. Yes, thank you very much all.
Yeah, thank you. So let me then move to the next presentation. So the next presentation is for the project 5G Heart. As you might deduce, this project deals also with e-health issues, but they also have a component on automotive, and this is the part that is going to be focused upon next. So let me briefly introduce the presenter. The presenter is Dr. Isaac Kim, a senior scientist at VTT. His focus is on 5G and beyond networks, and he was with Samsung Advanced Institute of Technology until 2006, and with NEC UK from 2008 to 2009. He received his PhD in communication systems from Lancaster University, and he is currently the vice chair of the 5G IA steering board. He is the coordinator of the project 5G Heart, and again he will focus on CAM related issues. So I give the floor to Isaac. Kim.
Can you hear me?
Yes.
Hello? Okay.
Yes,
so
go ahead.
Let me share my screen first. So can you see my screen? I don't know.
Perfect.
Which
Go
one
ahead.
is this one?
Yeah, it's the big one. Yes.
Okay. All right, good. Okay, thank you very much for introducing me. So my name is Hash Kim. I'm a coordinator of 5G Hut. Okay, in my talks, basically, I'm going to introduce the 5G Hut activity, and basically 5G Hut covers three main vertical trials: so healthcare, transportation, and aquaculture. In this conference, mainly focusing on the transportation, so I will mainly I jump into a little more detail about the transportation vertical trial of the 5G projects. Okay, so overview of the 5G projects. 5G Hut is one of ICT-19 projects. So this project is Action Types Research and Innovation Action. We granted 40 million euro from the European Commission. Project duration is 42 months. Due to the COVID-19, we extended the project duration by 6 months. So this project started June 2019, and it will be end next year, November. Actually, we are now in the middle of the projects. We have a 22 partner. This is project website. We are regularly updating the project's news and some outcomes. So if you are interested, please visit our project website. Okay, this is our project partners. We have a 22 partner all across of the Europe. So we research partner and big company and SME, and also in the healthcare sector, we have a hospital. In the transportation side, we have some big company and SME. So they are contributing to each vertical side. Okay. Yes, and this is objective of the 5G Hut project's main objectives of the 5G Hut is to define and validate 5G networks and to perform the multiple vertical trials. It's covering the healthcare and the transportation and also aquaculture. So we also have some sub-objective, and the sub-objective will be satisfied by the each work package, and that will be covers. Main objective, as I said, is performing the the vertical trials. Okay, then yeah. This is 5G hard ecosystem. As I said, we're going to cover the healthcare and transportation and aquaculture. We are expecting the good harmonizations among 3 different verticals. Let's say that we have one combined use cases scenario. This is combined between the healthcare and transportation. So there is a scenario like that. When there is some car accidents happen into the road, then the patients should go to the local hospital as soon as possible. For doing that, we're gonna using those 2 different the use cases and transportation and healthcare. In the transportation use cases, we can control the traffic control, then the traffic light. So the ambulance go to the local hospital very smoothly. That would be one vertical side will be helpful this scenario. And the other side, the healthcare part, we can install the 360 camera and the IoT device in the inside ambulance unit. So the first responder get some support from the local doctor. So in order to do this, we're gonna using the multiple slicing technique and also dedicated beamforming and so on. In addition to this, we're gonna start some business model as well. We have many use cases scenario, but another important aspects about this study is the business model. As I said, in order performing that transportation use case and healthcare use case, we are using the many network resources, dedicated beamforming, slicing, and so on. But we don't know yet who are willing to pay for this. So probably the hospital or local government or insurance company, they're gonna pay, but we are not so much clear. So we are starting business model in this project as well. Okay, then next. Yeah, this is the 5G facility. This pilot site is main 5 different countries. So Oslo, Kongsberg, Trondheim in Norway, Surrey in UK, Asten, Greece, and Oulu, Finland, and Trondheim in Netherlands. And we're gonna using the ICT 17 project, 3 different 17 project, 5G Bini, Genesis, and Eve, as 2 national 5G test platform. This is the 5G test network in Finland, 5G Groningen in Netherlands. In case of the transportation use cases, they will be mainly performing the Surrey in UK, and also in some of them will be performing the Oulu, Finland, and Groningen in Netherlands. Okay, then yeah, this is a very brief introduction about healthcare vertical. Healthcare vertical basically covering 3 use cases: remote interventional support, and field cam, and vital patch. So this is a very initial demonstration in Oslo University Hospital. This is ultrasound, some surgery experimentation. The local side, we can observing and control this robot arm. Then we can observe the ultrasound examinations. And this is a pill cam, very small pill cam. Is using this small pill cam so we can detect some colony or cancer inside the body, and that data is stored in outside the storage. But what you want to do is transmit that information directly to the local hospital server. So this is what I want to do. And the other thing is vital patch. This is a small patch that was developed by the Philips. Basically, one patient got a surgery, and then they're gonna stay in the hospital 1 or 2 weeks. But what you want to do is if you attach it, this vital patch, they go to the home so a couple of days later. And then remotely we can observe the patient's status and health condition using this vital patch. So this is one of our activity. Next is the transportation. You may be interested in this activity. So we have a main 4 different use cases: the platooning, autonomous assistant driving, and remote driving, and then the vehicle data services. So I will explain a little more details about the later slide set. Then next, yeah, this is aquaculture side. So we're gonna using the 5G technique for aquaculture, fish pump. So some people are asking me many times why the fish pump needed the 5G technique, but this is so much important issue. If you understanding some pain point in the fish pump, this 5G technique is so much useful. Especially you're gonna need to observe the fish's health conditions. Actually, one small fish got a disease, and that disease spread very quickly into 1 kg to another. So it is very important to to observing their condition, the fish's condition, and also that will be very helpful for environmental issues as well. Okay, then this is a timeline of a vertical trial. As I mentioned before, then we're going to extend it to this project to 6 months. We are now here. It's May 2021. So we are now in the middle, and some of the use cases already done. That some use case trial will be released in a couple of months. Project website and the project YouTube, so you can visit our website and YouTube clip. Okay, so we basically have the phase approach in the phase 1 and phase 2 and phase 3. Each use cases have a very little different types of a phase approach, but basically in phase 1, we're gonna performing that use case in the left side, very small scale. And the phase 2, we're gonna performing the long distance use case. Let's say in the Oslo University Hospital, they're gonna have some control unit, and local side Trondheim, they're gonna install the robot arm and examine the ultrasound examination. So this is long distance. And phase 3 is basically mobility test. So what is the ambulance unit? We can install some equipment, and then we can observe in depth, and then we can test the mobility. Okay, this is timeline. Yes. Then next is I will explain a little more detail about transportation vertical trial. First trial is the platooning. You know that. So the vehicle move like a train with a virtual string. So in this use case, we can reduce the distance between the vehicle and also reduce the overall fuel consumption. So to do this, we're gonna doing some see-through and the dynamic channel measurements for the traffic progressions. So these use cases will be performing in the Surrey side using the 5 Genesis. So main application of the 5 use cases will be the EMBB and URSC. Okay. The next is autonomous and assistant driving. So we're going to combine the sensor data and communication capabilities for advanced driving mode. As you know, the many accidents will happen in the cross section. So the T2S1 and T2S2, this is the autonomous and assistant driving. It will be covered the smart junction and network assistant collision avoidance. And also be a QoS and advanced driving and human tachography that will be covered with this. You may not so much familiar with this human tachography. I can explain a little more about it. Basically, we are using the wearable devices. The one driver have some wearing the smart watch. The smartwatch is to detect the driver's health conditions, and depending on the driver's condition, maybe they're gonna napping or they're gonna have some health condition is not so good, then we can give some proper alarm or some message to the driver. In some serious cases, they're gonna some stroke, when that information will be transferred to the local hospital, then it will be get some support from the nearby the first responder and the local hospital. And this is T2. This is autonomous and assistant driving. And next one is the remote driving. It will be done already very initially in the University of Surrey. They performing the remote driving a couple of years ago. So now in this project, we're going to improve the remote driving in University of Surrey. So remote driving concept, that the controlling the vehicle in the very long distance and outside or remotely, that the driver. So as you know, the key component is URLSC. So the latency is so much important issue, as you know that. The initial demonstration in University of Surrey that the latency was so actually not good. It's quite not so much a long distance, just the London between London and the Surrey. But even if that not so much a long distance, but the latency issue, then the car is it's not easy to control and they're going to the long direction sometimes. So we're going to improve that. Okay, then next is the vehicle data services, and the vehicle is connected in the 5G connection. So that we're going to get some different type of the services let's say the network will be the vehicle will be provided some more services using the 5G network. Let's say some location-based advertisements and over the edge over the air update. Let's say the car is using the many electrical and this information is needed. Let's say that they need some kind of maintenance needed and some parts should be changed, then that they're gonna get some information from the networks. And also some environmental will be covered by this use cases. And T4 use cases will be performing the 5G Genesis platform and the 5TN in Olo. Okay, then yes, I think this is all. So as I said, the 5G HUD is one of our 19 projects. I very briefly introduced 5G transportation vertical trial. And the interim result will be released in the project website and in a couple of months. And then you can visit our project website and you can find the latest outcomes. And this is our project partner. And there is some backup, some slide set. If you have any question, then I will answer it. Thank you.
Okay, thank you so much. Thanks for this presentation. And indeed, the transportation aspects are certainly very relevant to us. We see a very good commonality with the other use cases. So in that regard, it will be quite complementary. So I really recommend that people that are looking into use cases then go and check your website for further information. But with that, I thank you again, and we will move now to the next presentation. So
okay, thank you.
Could share. Thank you so much. If you could share again my screen.
How can I stop? Yeah.
It's okay. So the next presentation will be of Project 5G Drive, which is an ending project. And it will be presented by Xiaoyun Zhang from Dynec, Netherlands. Just a second. Xiaoyun is an ITS researcher. She received her Master of Science in Civil Engineering and Geosciences, Transport and Planning from Delft University of Technology, and the Bachelor of Science in Naval Architecture, Ocean and Civil Engineering from Shanghai Jiaotong University. Her interests are in intelligent transportation systems and related technologies, and she will present the China the 5G Drive results. So please go ahead.
Okay. So yeah, sorry for all the trouble. So my name is Uwe Herzog. I'm with Eurescom, and I'm the coordinator of the 5G Drive project. And in this presentation, we will present the project results that we have achieved in the area of V2x trialing in the scope of our joint trialing with the Chinese Twin project. And yeah, I hope Xiaoyun, who is the co-presenter, is going to join shortly so that she can then also participate. And by the way, Xiaoyun has been the leader of the V2x trialing activities in the project. Okay,
that's the brief. Full screen.
It is full screen, yeah. Sorry, it's not in presentation mode. Is it better now?
Yes.
Okay. So after a brief introduction that I will give, Xiaoyun will take over and go into details of the V2x trial. It will actually be much more than just result and discussion of that, because she will start with the motivation for the experiments and for the trials, and also present the trial setup and the details on the trials we have done, and then of course finally present the results that we have achieved. And at the end of the talk, she will then summarize with some lessons learned from the joint trialing between EU and China, and also give an outlook opinion on V2x in Europe. Okay, about 5G Drive. This is a research and innovation project in Horizon 2020. We are closely linked with the 5G PPP, although we are formally not part. And we have one specific aspect, and that is that we address two regions in the world. One is Europe and the other is China. And for these two regions, we try to bridge the current 5G developments through joint trialing and research activities. So it's both a combination of trials and a bit more forward-looking research. You can see here the list of partners. We have both academic institution and commercial partners. We have network operator. We have also one prominent user of the V2x work in the project, which is the BMW Group. And the project has started already nearly 3 years ago in September 18, and we are close to completing the activities in June, so in 1.5 months. And we have 17 partners from the 10 countries that you can read here. Having seen that, you might have two questions. One is, how can you do trials without equipment vendors? And the answer to that question is that the partners that we have in the project, some of the partners have very close relationship with equipment vendors, with manufacturers. And specifically here in the case, these are Nokia and Huawei, and they provide a trial infrastructure for 5G trials in EMBB. And the second question might be, how can you do joint trialing with China if you have no Chinese partners in the project? And the answer to that question is that we have a twin project in China. This is the 5G large-scale trial project, which is coordinated by China Mobile. I don't need to say much about this project because the presentation following this one will be given with a view from this project by Jilin Yi. So the presentation here will be from the angle, from the viewpoint of 5G Drive. We cover all types of equipment that is in a 5G network. So starting from terminals over the RAN, transport, network core, and also, of course, includes 5G services that, of course, are necessary if you want to do trialing. And in the figure that you see here, you can just see a simplified overview of what we are, how we are constructed. So you see the 5G Drive Consortium, 5G large-scale trial on the Chinese side. And our activities span from the more forward-looking research, so technical innovation beyond current 5G, through the joint trialing that we are doing. And a last point to mention is that for the joint trials, we have focused on two specific use cases. One of those is EMBB and the other is V2x. And that V2x will be in focus of the presentation today. On the right-hand side, you can see the bubbles, which should represent the trial sites that we have. The blue ones are those in Europe. And the ones with V2x are the ones in Espoo, as well as the GRC trial site in ISPRA. Okay, and with that, that's all for the overview on the 5G Drive project. I hope that Xiaoyun has joined meanwhile and will now be able to take over.
Which is a twin project of 5G Drive. The presentation will be made by Dr. Jilin Yi. She is the chief scientist of wireless technologies at China Mobile. She received her PhD in electrical engineering from Stanford University. She is chair of the ORAN Technical Steering Committee and ORAN Executive Committee member. She's also chair of the Future of 5G 6G SIG. chair of the WAIA, Wireless AI Alliance, Executive Committee. She has a tremendous activity and presence, and she won a number of IEEE ComSoc prizes. I don't need to further sell her. Please, Shilin, if you could present then the twin project, I would appreciate.
Okay.
Okay, go
so
ahead.
I
Go
will
ahead.
share my screen then.
Yeah.
So do you see the full screen from me? Hello?
Yes.
Okay.
Yeah, go ahead, Chilling.
So I guess following on Ulrich's partial presentation on the 5G drive, I'll be sharing from, I guess, the partner's perspective on this work. Basically, this is the twin project of EU and China on 5G, and composed of the 5G drive project from EU and the 5G large-scale trial project from China. And actually, I think the 5G PPP initiative in Europe has been very active from very early on in involving inter-regional partnership between EU and Japan, Korea, and Taiwan, etc. And then finally, I think this was 4 or 5 years ago, we started discussing the possibility of having a collaboration between EU and China. And then this twin project is basically the first outcome of that effort. And first, I think I'll give some background about the particular Chinese project, the 5G large-scale trial. In a way, this is our version of a PPP project, because the funding basically is a 1-to-2 ratio. So 20% from the government funding, and then 80% from the industry matching funds. And this is a project that started a few months earlier than the 5G drive project. Specifically, it was in June 2018, and it's concluded in December last year. Of course, we are kind of doing some wrapping up processing at this point, but the main work of this particular project has been concluded by the end of last year. A little bit of delay was caused because of COVID. Okay, initially, the target of this project was required to cover 3 cities with at least 50 sites per city, but in reality, for this particular project, we covered 5 cities and with 100 sites per city. Okay. And the partners, because the project here have a maximum number of partner allowed. So this one, we have a total of 7 partners, including the major vendors, Huawei, Ericsson, and Datang, as well as a very important intelligent vehicle pilot demonstration sites provider, the Shanghai Automotive City, and plus 2 very, I think, crucial research institute from different policy and regulatory departments in the government, in charge of the traffic management technology and the highway transportation and the policies and regulations research. In addition, for the more advanced R&D effort, this project also has BOPT as a partner. And the main goal of this project basically is first, is driving towards 5G end-to-end capability from the network planning, optimization, and all the way to OAM. And certainly, it basically goes through the trial phase to the pre-commercial phase, from the network to the terminal and to applications in all aspects. And in terms of applications specifically, the eMBB and the cellular V2X were the focus. And it's structured into basically 8 tasks, covering radio part, the RAN part, the core network, the transport network, the terminal, including the chips and the key components. And then from the application aspect, first the voice over NR and also other data services and a wealth of message services using 5G. And then in terms of vertical, in this particular project, transportation was actually the main focus. But of course, as everybody knows, this was mainly based on LTE V2X, not really 5G V2X, since the standard was not really finalized there. And so in the first year, actually during 2019, this project focused on getting both non-standalone and standalone basic performance ready. So by the end of 2019, we could say that even though the standalone started a bit later, but already caught up in terms of being ready through the experience of this trial, this project. And then throughout 2020, even with COVID-19's impact, we were still able to complete important standalone new features test and trial verification, particularly focusing on the 5G voice, which includes the EPS fallback and VONR, and as well as key challenges of 4G and 5G interoperabilities. Some of that I will highlight later. And then with this background, our joint twin project with 5G Drive, like Ulrich said, are making use of 5 trial sites, trial cities in China. I cannot see here, but it's including Wuhan and Shanghai and etc. And actually, Shanghai is where the V2X automotive V2X site city is based at. And then the 3 testbed in EU side, which I think Ulrich also highlighted, specifically one in UK, the other in Finland, and then one in Italy. And I think 2 of them have V2X covered, and 2 of them have eMBB covered in this case. And of course, we are using slightly different bands, as you probably know. In Europe, the 5G eMBB is based on 3.5 gigahertz, whereas in China, for China Mobile specifically, we are using 2.6 gigahertz and 4.9 gigahertz. And then for the V2X, is primarily at 5.9 gigahertz band. And this large scale field trial covered a wide array of typical scenarios for dense urban, for suburban, and for outdoor, indoor, as well as outdoor to indoor coverage. And also, of course, with a specific high value scenario that was a focus, which is high-speed rail, as well as metro line in China. And then this is a sample list of the trials and tests that were done, including the 2.6 gigahertz specific throughput and massive MIMO, as well as its latency in the both control plane and the user plane. And then 4G, 5G adjacent channel and co-channel interference is also an important consideration in 2.6 gigahertz. So it took a lot of work there. And then of course, energy energy consumption of 5G has been a serious issue globally. And so we, in this large-scale trial, we did a lot of work in improving the energy efficiency from the material and device and at the base station level, at the network level, and finally at the cross multi-rate cellular network level. And then in terms of 4G and 5G interoperability, there is a lot of details, challenge, and consideration that needs to be covered in terms of the handover or redirection or reselection under different situations between 4G and 5G, and including some of the globally identified faulty 4G terminals issue that makes the interoperability impossible. Basically, the faulty 4G terminal would fail to have access to the network altogether because of some shortcut in the implementation. And then I think I mentioned earlier, in terms of the 5G voice, there are two versions. One is the fallback to EPS. The other is the VONR. Of course, we can expect that the latency would be much better in VONR versus the fallback. And then for V2x use cases, I have to say that in this particular project, we did not really cover very sophisticated scenario. Primarily, it was focusing on GLOSA, the green light optimization, and also the intelligent intersection for pedestrian protection, etc. Okay, this is a little more detail for the testbed sites for the EMBB in our twin project. In China, it's a 5 city, and in Surrey, you have the 5G IC testbed, and then in Espoo, I think there is the VTT sites, probably very close to Nokia headquarters as well. So I suspect there is some collaboration there as well. And then for the V2x testbed, like I mentioned earlier, we have this Shanghai V2x Trial site, which is about, I think maybe 20 square kilometer area total, where it is supported by combination of LTE and DSRC. And but mainly right now, it's very well equipped for intelligent traffic lights facility. And then in Finland, there are V2x trial sites as well, hosted by VTT, and also I guess the JRC in ISFRA. This one was already mentioned by the previous presentation. Okay, so I'm happy to say that through about 2 years' time in this cooperation, there's a lot of active interactions and visits and joint trial between our team and the 5G Drive teams, specifically the end of 2018, as well as the first half of 2019, and all the way to the end of 2019. There were mutual visits at various cities in China and in Europe by the team members. So there's technical workshops, there is joint trial. It was very exciting, but until, of course, last year, all the activity had to shut down in terms of the physical visits. But in the process, there is also good fruit of labor on the research front. You can see that there are several conference papers as well as journal papers that was jointly delivered by these twin project teams. And so this is one of the paper in ICC last year. And that's another paper in the Open Journal of Vehicular Technology last year as well. Okay. A lot of the results from this large scale trial actually was very useful. I'm just giving you some sample result here. these are all being put in the guidebook for China Mobile's large scale commercial deployment of our 5G network. So this is current state in terms of our actual 5G network based on those guidelines. We have deployed so far, I mean, by the end of last year, we have close to 400,000 standalone 5G base stations deployed in China, in China Mobile's network, which covers all the county level and above cities. So it's over 330 cities there. And its coverage is also impressive in that it's a 3D coverage. It goes as high as 6.5 kilometers above sea level, which is basically at the most advanced boot camp of the Himalayas mountain range. And then as low as more than 500 meter, more than half a kilometer underground. This is part of a 5G vertical application in the minefield underground. And there is, I think, close to currently 100, I mean, close to, I cannot really see here. Let me see, I can, yeah. Close to 100 million 5G terminals already users in our network. And also last year, even though COVID-19 did have impact on many of our progress, but it actually accelerated the demand of deployment because some of you might have heard the news of how 5G connectivity become so timely and so useful to provide the kind of connectivity with high bandwidth and low latency for various applications that was needed. So I'm not going to spend time on that here. And of course, I know that today we are mainly talking about verticals. And just so that you know, we have been working with 15 different vertical industries that's identified here. And we have developed 100 plus nationwide projects and 2,000 plus provincial level projects that are close partnership with various vertical industries. But to be frank, I don't think that there is large scale deployment of any of the vertical applications yet. And I saw some of the earlier presentation today investigating the business model. I think that is a great effort because 5G brings a lot of possibilities in terms of technology. But I think to really make 5G a powerful enabler for verticals, we do need to have a lot more work in the new business model development. Okay, before I finish, I just want to mention a few words about the machine learning and AI capabilities. Here, I'm showing you a list of sample deployment trial or tests of various machine learning AI enabled function, including cross-layer optimization, including the network capability enhancement, as well as potentially the network capability exposure, all enabled with machine learning and AI algorithm. And the sample here I'm showing you are the cases where we actually have either deployment or trials in different provincial operating companies already in our network. And we believe going forward, whether it is for V2X or any other verticals, this particular direction would be very important. And actually, we believe that from application down to management domain to control domain, all the way to scheduling and even physical layer, there are various opportunities that are at a different level of maturity for commercialization. And this is basically an essential, I think, element for us to go from 5G to 6G. Okay, with that, I will conclude my presentation today. Thank you.
No, thank you, Shilin. I think you have given a very good perspective of the developments in China, and ending with the transition to 6G. I think it's very, very timely. It is again extremely interesting to have these twin projects. And again, as it was mentioned, even if there are no common partners, they were able really to coordinate, and this is really impressive. That was the whole point of the exercise. So again, Shilin, thank you so very much. And I hope now we can conclude the 5G drive. So I don't know if Xiaoyun is there or not.
Yes. Can you hear me, George? To begin her presentation first. So I guess 5G drive and V2X solution results achievement will already show this first few slides. Here is the table of content. Well, Wu has given the 5G drive introduction. I will take the later three parts: the results discussion, the lessons learned of joint EU-China V2x trial, the outlook of the future V2x in Europe. So without further ado, I will slice to the motivation of work package 4. In 5G drive, work package 4 is V2x development and trial. For the motivation, I will just mention a few here. We all have the background in mind that CV2X is initially defined as the LTV2X in 3GPP release 14. It was designed to operate in several modes. The ad hoc communication via PC5 interface was introduced in D2D mode, which is quite interesting with its promising low latency and the requirement for the future of connected and automated mobility. With this, we try to see if CV2X has the potential to redefine the transportation, providing real-time, highly reliable, low latency data flow to enable CITS applications. Quite a few would be involved to traffic safety, traffic efficiency, and a few others. CV2X, we try to see whether it paves the way to connected and automated mobility, and that's why we also involved the autonomous driving vehicle in the trials. So with these few motivations, we begin to identify our objectives for the work package 4. There are quite a list of objectives. Today, the ones that are involved in the later on results discussion are listed here. One is to define the joint V2x use case together with Chinese partner. This is one of the first, as Qilin already mentioned earlier. The second, to joint trial and demonstrate these joint use cases. This is very ambitious as well. The third one, we want to ensure the feasibility and then, if possible, compare the performance of LTE V2X on those KPIs like latency, communication range, the feasibility to support connected and automated mobility via LTE V2X enabled application. Where Qilin also mentioned we are doing the GLOSA, green light optimizer, speed advisory, and also the intersection safety on the vulnerable road user, or either on the intersection warning, intersection collision warning application. So I will go further. Before I start the results discussion, I want to mention some results preview, which will be included in deliverable 4 end of May. this year's version. The results on this slide, I will not discuss it in detail today, but nevertheless, they are very interesting results. I will name them just in advance. So one is the frequency jamming attack and the misbehavior detection system tests. So before we go into the trials, we did quite a few laboratory tests of, on the vulnerability of LTE V2X and the vulnerability of current technology, the ITS-G5 in Europe. We perform some tests there and see if there's any vulnerability and to make assessment of how good they are performing. We also did a laboratory test on the conformance test of ITS-G5 and on LTE V2X. On top of that, we did a coexistence test on these two technology because let's like it or not, we are in Europe with these two technology in parallel for now. We also did some auxiliary studies, and those are the fields that are related. The simulation of V2x communication utilizing mobile edge computing, the key V2x link budget parameter on the field trial results so that we can use the most optimal configuration when we are performing trial. The hybrid positioning for automated driving complemented by C-V2X communication. This is also quite interesting. Later on, I will give a presentation on the paper, which also detail this a challenge that we identify. So no further ado, I will begin a deep discussion on the results of joint EU-China V2X trial. As I just mentioned, joint EU-China V2X trial is over continental, and without mentioning, we already feel the challenge there. To start this, we begin by contacting the right person in a 5G large-scale trial. V2X teams in 5G large-scale trial, we are performing and identify before performing the trial to identify the use cases together. So in joint EU-China V2X trial in Europe, we did 3 categories of tests. Initial quality test, which is testing the reliability of LTE V2X assisted connected and automated driving. Second category, performance of LTE V2X. There we have designed several test scenarios. Each one of them are highlighting one of the impact factor. For example, the number of LTE V2X stations, the vehicle speed, the antenna height, and see what the performance of LTE V2X technology, basically judge on the KPI of latency, coverage range, and the packet error rate. For the third category, both Europe and China, I mean the 5G Drive project and the 5G large-scale trial, we featured 2 day 1 CITS use case services. One is intersection safety. In Europe, we did the intelligent intersection with vulnerable road user crossing and camera detection. The other one is GLOSA. We try to provide individual speed advice to connect an automated vehicle utilizing the LTE V2X communication. On the 5G large-scale trial site, they have also categorized 3 categories here. One is the interoperability test between different vendors. The other is the V2i V2v Coverage Test. The last but not least, LTE V2X performance test, just like what we did. We have the 2 featured joint EU-China use case, but they have among their 17 day 1 CITS services, those 2 are joint cases together. On the intersection safety case, they mainly perform the intersection collision warning with vehicles at the intersection where they have blind spot to see other vehicles. So I will start with the joint EU-China V2X trial in Europe first. We did the trial preparation. First, you can see here is the trial architecture. And here is the map of the route where the connected automated vehicle is going to drive. The automated vehicle starts from 1 kilometer away from this intersection, approaching this 4-way intersection. You can see here the green part is the LTE V2x roadside unit. Here you have a small hill and quite a few greenery along the route. Here is the 5G base station. And on the connected and automated vehicle, we have the LTE V2x OBU onboard unit. So here is the architecture with a snapshot of this intersection. You can see that when the vehicle is approaching, the system architecture here basically applies to the two use case, GLOSA and intelligent intersection. You can also see that for us, we did for each of the use case two scenario. One is to communicate directly via 5G. So imagine the pedestrian walking and the camera capture this, and the information will be sent to the cell tower, to a back office, which will be sent over the 5G network to connected vehicle to warn him when he turns with the green still need to mind the vulnerable road user. That's one. The other would be what we are really interested is the ad hoc communication based on LTE V2x technology. So when the pedestrian is walking, the camera detect his presence, send a CPM message to the RSU here, that is the LTE V2x, and via ad hoc, he sent to the OBU on this vehicle to warn him within, of course, we expect later, much less latency to warn him that the pedestrian is crossing. So I just mentioned one of the use case. The other one applies as well. We did it in two of the scenario. One is the 5G network, and the other is the direct communication via PC5 interface. So I will start to show some of the interesting results we have. We did initial quality test. Here you can see that we are trying to trial the reliability of LTE V2x. We started from some raw data, and after data analysis, we presented in this color map the latency. And also in this histogram, you can see the message size we are trying to transmit and receive. You see the latency distribution here. Here we have listed two of the scenario we try out, the 5G latency and LTE V2x latency. The latency here means the server to the connected automated vehicle or the RSU to the OBU with the same LTE V2x technology. We tried to variate the message size here. You can see the mean latency for 5G cases is mostly around 40 milliseconds. For the LTE V2x, it's somewhere smaller, also a little bit lower than 40 milliseconds. And you can also see the lost message are non-existing. The jitter is a little bit higher for the 5G latency, which might be due to the not state-of-the-art 5G network at the trial site. But we are not focused on the comparison here. So we mainly want to see whether this is feasible and whether the reliability of this test setup is good. The second one, we try to do the second category of performance of LTE V2x. We have the first assumption. The number of emulated stations can affect LTE V2x average latency. We did a trial design. We try to increase the number of emulated stations by decreasing the message interval. Since we don't have a physical stations, we only have one OBU and one RSU. So we tried by message interval from 1 milliseconds, 5 milliseconds to 150 milliseconds. And by that sense, the emulated station was increasing from this side to the left, from 7 to 1,000. In each of the case, 5G and LTE V2x, you can see that the latency, if we are increasing the emulated amount of stations, the latency highly increased or jump around quite a few when in the case of LTE V2X, the latency is somewhere stable around 25. And when it's really high amount of stations, we are trying to emulate it increase to 32. Here is a color map. This on the left is the 5G one. On the right is the LTE V2X. You can also see the performance are quite stable once you have entered the coverage range of LTE V2X. On the other hand, this is probably due to a handover between towers and not that optimal. So the second assumption is vehicle speed can affect LTE V2X average latency. We designed the trial to increase vehicle speed. Since we are on the public road and did not close the road to do all of the trial, we can only vary it from 10 kilometer to 40 kilometer, and this is urban road, so we need to apply to the speed limit here. The results show that under urban driving condition and speed, the impact on LTE V2X latency is not that observable. So here you can see most of them, when we are increasing driving speed from 10 to 40, the mean latency is 24, 25, and very stable. The last assumption, we are trying to vary the antenna height, and we think that can affect LTE V2X average latency greatly. We increased antenna height on RSU from 1.4 to 3.8 meter. And by the height, I mean the I will show the picture here. This is the height of the antenna. We tried 3 of the position, and the height on the vehicle is already fixed, is right on the roof here. So it's 1.8 meter. Let's see the results. We see that when the antenna on the RSU are increased, the mean latency decrease, and the packet loss rate also decreased quite a lot. I'll talk about the featured joint EU-China use case. I already had a quick description on the intelligent safety use case, and for the GLOSA use case, we are performing on the same test route. This time we developed an application to provide individual speed advice to the automated vehicle. And if the driver follows the speed advice, we are hoping that he does not need to stop for red traffic light, but to go through during green phase. And this is to increase the not only traffic efficiency, but also the comfort level of the driver, and also to increase the safety where the driver doesn't need to take over control once this application in the future integrated to the vehicle. So the results shows that for baseline without speed advice, the connected and automated vehicle will stop for 60% of the time. The success rate to go through green phase naturally would only be 40% of the time. And for an enhanced study with the speed advice, the individual speed advice to this vehicle, which means that the spot message, the signal phase and timing from the traffic light controller is already sent from the LTE V2X RSU to the vehicle OBU. And the vehicle OBU take the time to green and calculate the speed to pass through green phase. And with this enhancement study, we see the success rate to pass through green is 90%, which is quite promising, considering we are also on the open road, and that was a busy road that day. If there are pedestrian crossing or any vulnerable road user, we have to stop for them, and that would be affecting the trial result quite a bit. But the result shows quite big improvement on this condition already. I will go into the joint EU-China V2x trial in China. Their trial is performed in Shanghai. As Qilin mentioned, it's 20 kilometer, around 20 kilometer in a closed road and open road area. The first category of test they did is the interoperability test between different vendor. They did two subcategory, and one is the one RSU transmit spot and multiple OBUs from different vendor receive. The other would be one OBU transmits basic safety message and multiple RSUs from different vendors receive. Both are successful, which identify that the interoperability of different vendor equipment are feasible and according to the conform to the requirements. The second category they did is the V2i V2v coverage tests. There are also two separate subcategory. First one is the V2i, where the OBU to RSU coverage test under a non-line of sight situation is performed. You can see that here is the PLR to distance relation in the non-line of sight environment. The x-axis is the distance, the y-axis is the packet loss rate. For two different vendor equipment, we can all see that around somewhere 800 meters, the packet loss rate would be higher than required, more than 10%, which means the coverage is around somewhere 800 meter. The second category, OBU in the test vehicle was moving away from RSU, and the RSU is installed 8 meters above the ground level on a light pole, and this test is also successful. For the coverage test, which is the second category, V2i V2v coverage test are also separately performed in two of the sub-use case. One is V2v, OBU to OBU coverage test under both the line of sight and non-line of sight. They perform it under driving mode and also under fixed position mode. It all show that OBU to OBU, so vehicle to vehicle, under near point, far point, the latency mean is somewhere around 16 milliseconds. And far point by that is the 400 meter. The PLR, the packet loss rate, is 0% and quite good. Under fixed position, the OBU to OBU distance is here showing 400 and 450. The mean latency is still somewhere around the 15 milliseconds, 18 milliseconds. But the PLR rate is significantly increased once it is above the 450 meter, which is also the case in European side. Once we have the we enter the coverage range, PLR rate is quite good. Otherwise, once it's out there, out of the range, the coverage, the PLR, the packet loss rate will be increased sharply. This is almost the last one. So we did they did the LTE V2x performance test, which are also two of the jointly defined use cases. On the intersection safety use case, they tried to perform with a system architecture showing in this picture. You can see the host vehicle view of remote vehicle 1 is blocked by remote vehicle 2. So the intersection, the vehicle vehicle 1 is trying to send a BSM message to host vehicle to warn his in the collision route with a host vehicle. And the other one is the GLOSA use case. I have not translated this into English yet, but the system architecture is basically also the same with the European one. The traffic light controller sends spot message to the RSU. The RSU are trying to send via the PC5 interface to the same technology, the LTE V2x OBU, and OBU receive it. So it is it received the spot information, which means he knows how many seconds later it's going to be red or green or amber. We have the results. One OBU and one RSU transmitting. The latency is smaller than 25 milliseconds, which also apply to the previous two category of tests. the packet loss rate is smaller than 10%. When they increase to 20-ish physical OBU and RSU, which means that they also have the equipment of 20 OBU and RSU, the latency is smaller than 38 milliseconds. The packet loss rate is still less than 10%. And with this, I go into the last slide, which is the lessons learned and outlook. The joint EU-China V2x trial, I would say in the beginning it is quite difficult to collaborate because we are going without a roadmap. This is one of the first time. So without any previous experience, we are also trying to find how to collaborate. Once we have aligned our ideas by the beginning of 2019, everything seems to work fine. We had ambitions to trial together the joint use case in one location, either in Shanghai or in Europe. But this is disrupted by the pandemic. Once the pandemic hit, we cannot join face-to-face. But right after that, we developed the pandemic resilience plan. So the former plan, we transform and transfer it to the online format. We try to follow the joint EU-China V2x trial framework. Either of the party, when they are performing demos, we tried live streaming via different kind of channels. And we also perform quite a lot of joint work report, such as the last report, deliver 4.4 in our work package, a lot of publications, papers and articles, and quite a few events and workshops. For the post-pandemic outlook, I see that online collaboration is becoming the new norm. We both in Europe and in China agree the potential of CV2X. It is the basis for the future of connected and automated mobility. We all look for the added value of the future work, whether we can see the application of CV2X in the fast-growing connected and automated mobility frontier. Also in Europe, we see that we are not as rapidly developed as the Chinese state of play. While they are having a big 5G large-scale trial rollout, we are still seeking the penetration point of CV2X development. And today, my presentation would just be a snapshot of what's really happening on the trial site. So I hope this could be somewhere a breaking point to really begin the CV2X development and the rollout in Europe. And thank you all for your attention, and that concludes my presentation.
Thank you so much. Thanks for your presentation. I understand that due to the difficulties, we finished a little bit late. Again, I just want to